We are on chapter 6. We'll study about the work and work done by a constant force. The force is not changing, it remains the same. Now let's say, for example, we pushing or pulling a car. There is some work done, which is work equals force times displacement. So we could write down W, which is work, F times S. The unit of force is Newton meters. So you can look into table 1, page 143, and you can go over the units used to measure force and work. We are now in the second page, where force is acting on at an angle theta, which is the angle it makes to the horizontal. So we have to find the horizontal component. Theta is not 0. If theta is 0, then it is force times the distance. But here you have a component of x, which is f cosine theta. So this displacement is now W equals f times cosine theta. So they go over the example, which is on page 144, example 2 and 3. Now look at this. You have somebody is pulling the hand carry at an angle theta, the force acting here diagonally. So the component will be f cosine theta. These are the units we use to measure work done, SI, CGS, and BE unit wise. So you can go over that, but mostly we'll be using SI unit to solve problems. Now we are on chapter 6, section 2. We'll be relating work and energy theorem it is called, and the kinetic energy. The force acting perpendicular to the work on the object, which is always what type of effort you put. In other words, the change in the kinetic energy takes place once it moves. And this theorem is work energy theorem. In this page will be referred to, or rather figure 6.5 will be deriving a relationship how the kinetic energy initial and final is derived. So the first place, sum of all the external force times S, which is Fs as we define the work. Now that equals F equals m times a, mass times acceleration times s. So work done is net or total external force. Now look at this equation we have. V final square equals V initial square plus 2as. That is the first, chapter 2 equation, one of the 4 equations we studied before. So we can have more precisely, AS is half V final and V initial. I left the square sign here. Actually it should be half V final square V initial square. That's how we come up with work equals F times S, half mv square, which is final, take away half mv square initial. So this is the first term we have is the final kinetic energy, and the second term we have initial kinetic energy. So right side you have two terms which are kinetic energy, and now look at this. We have mass times half mass times speed square, which is the unit wise it's joule. Excuse me. So we define now, as you see, the kinetic energy equals half mv square. Unit is in joules. So work done W is Ke final and Ke initial, the difference of these two. So that's in terms of now here mass and velocity, mass and velocity. This is work energy theorem. You can go over example 4, page 147. Now we come in across another energy which is which is known as gravitational potential energy. Look at the figure we have, 610, page 152. Potential energy is dependent on the height where the object is situated, but kinetic energy depends on the velocity at which the object moves. So we have now force due to gravity, which is mass times acceleration due to gravity, and displacement, as you see in that figure, we have initial height, take away the final height, so that's the difference. Now we already defined work equals F times cosine theta times S. Here theta equals 0 degrees and your F is mg, which is mass times acceleration due to gravity. So finally we get work done equals mg in parentheses h0 minus hf, difference in the height. So greater the value of h, greater the potential energy or potential to work. Okay. So gravitational potential energy we defined. Work done due to gravity is gravitational potential energy, which is initial, and gravitational potential energy, which is final. Difference between these two will give you change in potential energy. So we define that equation to be simply P equals, or potential energy equals mass times G times H. please refer to the figure we have 613 on page 153. We have to define now two different type of forces. One is conservative force, other is non-conservative force. Okay, for the conservative force, work done on the moving object is independent of the path. So the work is not dependent on where the object is moving. There is another way to define this also. A force is a conservative force when no work is done on the object when moving around a closed path. Okay, depend on a closed path. If there will be no work done, that is conservative force. And non-conservative force is totally different. Look at this. A force is non-conservative if the work it does on the object moving between 2 points depending on the path. So the work should be done between 2 points. So work non-conservative NC depends on K, delta K and delta P. Look for table number 6.2, page 155, where you find the examples of conservative and non-conservative forces. You can look yourself. Now, the next topic is 6.5, conservation of mechanical energy. So mechanical energy total is sum of kinetic and potential energy. So that is work done non-conservative force. Now look, Ke final take away Ke initial difference plus potential energy final, potential energy initial difference is that. So now we'll organize KEP, KEP, KEP final, KEP initial. So work done non-conservative force wise will be energy final take away energy initial. That means the energy is conserved here, where you have E final equals E initial, and the total E final is total of kinetic and potential energy, and initially the same thing. You take into account K and P initial. Go over please this example 8, page 157. Now we are on the last section, which is 6.7. We define the power. Power is work over time. Unit is watt. So P again change in energy over time. So if you divide work over time, on this side you have force times S over T, because work is F times S. Then finally you will end up with P equals F times V. You can look into table numbers 6.3 and 6.4, page 161, to have a better look. Most of the problems will be very simple in this chapter 6. So we're talking about now to review kinetic energy, potential energy, then mechanical energy, conservative force, non-conservative force. For conservative and non-conservative force, you will have no problems. Matter of fact, mostly you should focus on work, kinetic energy, potential energy, conservation of energy, and power. These are the important topics to attack the problem. And I believe you have enough of homework problem to do, and also you have the examples in the book. That should be enough to prepare for your exam. I'm half through your exam 1. I'm not finished yet, but I finished your homework. Homework assignments are all good. They're 100% correct, and you guys all did a good job. Tonight, hopefully, I'll finish the rest of the exam 1, which I'm planning. I was a little busy over the weekend, I couldn't do it. And promise it'll be done in a day or two. Thank you very much. Have a good night.